Technology of China, and he's going to tell us about observation of random molecular Feshbach resonances and ultracold temperature.
Okay. Okay, good afternoon, everybody. First of all, I would like to thank the organizer, especially Kang Kun, for inviting me here to speak about our recent results. Observation of atom molecular Feshbach resonance at ultracold temperature. Okay, let's start from the molecular coherence. In physical chemistry, very important goal is to study the molecular coherence at the quantum level. So in theory, you only need to solve two problems. The first is to solve the potential energy surface. This can be done by solving the multi-electron Schrödinger equation for fixed nuclei configuration. After you have obtained the potential energy surface, you only need to simulate the dynamics of the nuclei under such a potential energy surface. However, theory is too complicated. We have to do experiments. Okay, so the conventional method to study molecular coherence is the molecular beam scattering. We already have two talks on molecular beam scattering. They can now study state-to-state coherent dynamics. So I do not need to talk too much about it. What I want to mention is that in conventional molecular beam experiments, the temperature is usually quite high. It's about a few hundred Kelvin. So at such a high temperature, many partial waves will contribute to the scattering cross-section, and the molecules are usually prepared in many internal states, and the wavelength is short. So consequently, quantum phenomena are difficult to observe. To solve this problem, cold molecular beam experiments are developed. We usually study the coherence at a temperature of a few Kelvin or sub-Kelvin. So when the temperature is reduced, the effects from higher partial waves are suppressed, and the molecule can be prepared in a certain low vibrational state. At low temperatures, the wavelength is longer or comparable to the interaction range, so the quantum mechanical effects manifest itself. So one of the most important quantum phenomena that has been intensely studied in molecular beam experiments is the scattering resonance. It occurs when the coherent energy coincides with the bound state of the potential energy surface. So when it happens, a long-lived coherent complex will be formed, and then the scattering cross-section is largely enhanced. So the scattering resonance directly probe the low vibrational state of the potential energy surface, and scattering resonance is extremely sensitive to the details of the interaction, so it's an ideal probe of the potential energy surface. In last 2 decades, there are many experiments studying the coherent resonance with molecular beams. These include the atom-molecule reaction and atom-molecule ionization, and atom-molecule inelastic coherence, and the molecule-molecule inelastic coherence. However, in these molecular beam experiments, the temperature is still high, and a few partial waves contribute to the scattering process. So the ideal situation to study the quantum effects in molecular coherence is to cool the molecule to nearly absolutely zero temperature. So in this case, only one partial wave contributes to the scattering process, and the molecule can be prepared in a single quantum state, not only the low vibrational state, the electron spin and also the nuclear spin can be polarized. And at such a low temperature, the wavelength can be much larger than the interaction range. So consequently, clearance at ultra low temperature is highly quantum mechanical. It's expected that scattering resonance is a rule rather than exception. So for the light particles, it is computational possible. So there are many predictions for this system. However, these predictions remain to be experimentally tested. The major problem is a cooling molecule is extremely difficult. So there are many methods that have been developed. However, to obtain ultracold molecular gas is still difficult. So currently, the only ultracold molecule that can be created in the lab is the alkyl metal diatomic molecule. Since the pioneering work in Gila in 2008, the first ground state molecule, RBK molecule, is created. Recently, different other alkyl metal molecules are created in different labs. So to create such ultracold diatomic molecule, we first prepare the ultracold atomic mixture, and then associate the Feshbach molecule, then transfer the molecule from the Feshbach state to the vibrational state by stimulated Raman adiabatic passage. And so after the first RBK ground state molecule is created, then they studied the clearance between molecules and also between atom and molecules. They found that for the reactive clearance, the loss is universal. So the short-range loss with near unity probability suppress all possible resonances during the clearance. So to study, in order to study the scattering resonances, we have to consider the non-reactive clearance. Oh, sorry. We consider the atom-molecule clearance. So there are 10 candidates. For lead system, lead system have some properties. First, the molecules are very heavy, and the potential energy surface is very deep. And there are many closed channels that can contribute to the resonant states in the clearance. So consequently, the clearance for this atom molecule clearance is highly resonant. If we consider the nuclear spin and the electron spin degree of freedom, then the computation would be extremely difficult. So in this paper, by Merritt, etc., they suggest that instead of calculate the single resonances, we can use a statistical model to estimate the density of resonant states for such highly resonant scattering. So they calculate the resonant states using the statistical model for these 10 combinations. They found that the density of resonant states is very high, but they also found that if the temperature is below 1 microkelvin, then S-wave resonances may be resolvable. And if we search for the resonances by sweeping the magnetic field, the statistical model suggests that there will be many resonances with the distance between neighboring ones is below 1 Gauss. So for our system, the molecule is an NAK molecule, and the atom is a potassium atom. They have a deep potential energy surface, and the statistical model predicts 1.2 resonance per millikelvin. And if we search the resonances by sweeping the magnetic field, the statistical model predicts 1 resonance per Gauss. So in this paper, they suggest to mirror the resonantly enhanced loss features in the atom-molecule mixture by sweeping the magnetic field. So in our experiment, we prepared the molecule in the low vibrational ground state, and the atom in 9/2 hyperfine state, and then we search for the Feshbach atom molecule Feshbach resonances by sweeping the magnetic field. So this is our experimental setup. We create a cold sodium flux and potassium flux using Siemens LoRa and 2D mode, and both of them are captured by dark mode in the main chamber, and then we transfer them to the magnetic trap and the optical double trap to evaporatively cool them to ultra low temperature. And this is the result of the degenerate burst film mixture, where we can get a temperature of very low, of 200 nanokelvin. So after we create the ultracold atomic mixture, we needed to find out some Feshbach resonances to create Feshbach molecule. There are many SV Feshbach resonances between sodium and potassium. Okay, and this is how we create Feshbach molecule. We use Raman photo association and to associate the molecule from associate Feshbach molecule from the scattering state. So the left figure is a typical result of association spectrum. The blue higher peak is the atomic peak, and the smaller red peak is the Feshbach molecule peak. The distance between them is the binding energy of the Feshbach molecule, and we can also dissociate the Feshbach molecule, and the right figure is the dissociation spectrum. Okay, so after we create Feshbach molecule, we have to transfer it to the low vibrational ground state. We use the same line as MIT used. So the pump light is the wavelength of the pump light is 805 nanometer, and the wavelength of Stokes light is 567 nanometer. Both the lasers are locked to the ULE cavity to narrow the line waves. And this figure is a typical result of the stir-up, because we can only detect the Feshbach molecule. So after the molecule are transferred to the ground state, we cannot observe anything. And after the second stir-up, then we recover the molecule signal. In our experiment, the maximum 1-way efficiency is about 7-8%. Okay, now we have to find out, you have to use work at atomic Feshbach resonance, near atomic Feshbach resonance, and we choose a window between 100 Gauss and 104 Gauss, so that the Feshbach molecule can be efficiently created, and the ground stir-up transfer is also efficient. So there are 36 hyperfine levels for the low vibrational ground state, and we choose 4 of them by choosing a different intermediate states, and also the polarization of the lasers. The molecular hyperfine levels are labeled by 4 quantum numbers. The first 2, 0 are the vibrational and the rotational numbers, and the third one is the projection of the nuclear spin of sodium, and the last one is the projection of the nuclear spin of potassium. Okay, this is our experimental procedures. We first associate Feshbach molecule, and then remove the sodium atoms. After that, we transfer the molecule to the low vibrational ground state, and hold the atom mixture for a short time, and then remove the potassium atoms, then transfer the molecule back to Feshbach state for detection. So in this experiment, we can prepare the potassium atoms in 5 different hyperfine levels. So in total, we have 20 spin state combinations. We measure the decay of the molecule, from which we can extract the loss rate coefficient. So at each magnetic field, we measure the loss rate coefficient. Here, for this channel, 0, 0, minus 3 over 2, minus 2, and when the atom is in minus 7 over 2, we can see that the decay is changed by the magnetic field. So, okay, we tried 20 spin combinations. So in most cases, there is no resonant loss features. But for 3 of them, we do observe these resonantly enhanced loss features. And the Gaussian fit gives these 3 figures are the Gaussian fit results. And currently, we found that these 3 loss features are all at about 101 Gauss. So, to expand the magnetic field range that we can study, after create a ground state molecule at a magnetic field of 102 Gauss, we sweep the magnetic field down to a desired value and hold the atom molecule mixture for a short time, and then remove the potassium atoms, and then transfer then sweep the magnetic field back, and transfer the ground state molecule to Feshbach state for detection. In our system, a sweep magnetic field is not straightforward because the system will cause anti-currents which will induce the residue magnetic field. So to compensate this residue magnetic fields, we using the so-called pre-emphasis method by programming the current of the magnetic coils. Using this method, we can sweep the magnetic field in a few milliseconds. This is an example of sweep the magnetic field downwards for 30 Gauss, and the stability of the magnetic field is about 200 milligauss. Okay, so this is our time sequence. So the hold time of the atom molecule mixture is about 7 milliseconds, and the total time is about 30 milliseconds. Okay, so here we plot the remaining number of molecules as a function of the magnetic field. And in the magnetic field range between 43 Gauss and 120 Gauss, we observed 8 new loss features. And the loss features, here we choose the molecule state to 0, 0, minus 3 over 2 and minus 2, and the atoms are in minus 5 over 2, minus 7 over 2, and minus 9 over 2 in 3 hyperfine states. So in these three channels, we observed 8 new loss features, and the loss feature at 101 Gauss is confirmed using this method. Okay, to make sure that the loss takes place at the desired magnetic field, but not during the ramping of the magnetic field. So we may also measure the ratio between the number of molecules for long hold time and the number of molecules for short hold time, and we obtain due to losses due to the atom molecule clearance at the desired magnetic field. So in total, we observed 11 atom molecule Feshbach resonances. The observation of atom molecule Feshbach resonances is just the start. There are still many open questions to be answered. And the first one is what's the density of resonant states. The statistical model predicts that the resonance, we should observe resonance, one Gauss, one resonance. However, in our experiment, we didn't observe so many resonances. And the second question is, what's the role of the nuclear spin in the clearance? Because theory cannot consider this in the theoretical model. This have to be done by detect the clearing products. And the last one is, can we employ the atom-molecule Feshbach resonances to associate the triatomic molecule as what we have done for two-atomic molecule? Okay, this figure is our recent results. We have tried more molecular hyperfine states, and now we have observed 40 loss features, more than 40 loss features. And different, in the figure, different color represent different hyperfine states. And the green one is represented the absolute molecular ground state. And this solid line represented the Zeeman splitting of the potassium atom from bottom to up. It's minus 9 over 2, minus 7 over 2, minus 5 over 2, and minus 3 over 2. When both the molecule and the atom are prepared in the absolute ground state, we still observe a resonant loss feature, enhance the resonant loss features. Well, this means that in this system, there is no so-called sticky clearance. Okay, this is our team. Our lab is led by Professor Jimmy Pan, and here are the students, and some of are the left. Jinrui is now in Imani's group, and thank you for your attention.
Question?
That's good.
So you saw in the previous talk that calculating the density of state
Yes.
would be not
So high, yeah.
lower. And we saw that already the density of state is lower than expected. Can you expect that you observe a lower number of Feshbach resonances
Because of the density of random
space?
space?
It's overestimating, exaggerating the number of resonances?
I don't know, because I cannot exclude the possibility there are many very narrow resonances that I cannot observe. So I can only say what I
It's an
measured.
open question both from the experimental and theoretical point of view.
Theoretical point of view, I don't know. I have to trust the science. Okay.
Yeah, but it's consistent with what Thais was saying, right? It's consistent. It's no.
At least it's not that dense. This is consistent with the science talk. Yeah.
Well, I don't think Thais really had a calculation.
Okay.
Yeah, but I think.
It was certainly very accurate estimate of density of state.
Yeah, so right now there is no theory, right, for the prediction of those positions.
It's just too difficult. For example, as I talked in BATS, there is a paper in 2017. They calculated the density. They calculated the resonance for K2 plus K plus RB clearance, and they cannot consider the nuclear spin of freedom. Cannot consider the external fields. So this calculation is done at a zero magnetic field, and with the total angular momentum is 0. And they give some results, and Thais also used these results, and he said that the results in this paper is different from, is 2 orders of magnitude smaller than this John Barnes paper, yeah, the paper from John Barnes. Yeah, from this paper. It's just too complex.
I think we just need some data, good graduate student. That's what we need. So yeah, come to theory. I mean, there are exciting things to do, right? I mean, we have all the numbers, And if we have, graduate students that work hard, I mean, this can be done, I think. Somehow.
We need a supercomputer.
So how far away are these collisions already from the you don't, obviously you don't see universal law, but there's some
How far? Yeah. Here is the loss rate coefficient. As far as I can remember, the universal rate should be 13. Universal loss should be 13 here. Yeah. 13 10 minus 11 centimeter per second. Yeah.
So this is much faster than universal.
I think we should not directly compare the measured number with a theory, because it's extracted from this formula. The density is actually not accurate, and I don't think we should directly compare.
Any other questions? Then let's move on.